let's look at what work is in physics. In everyday life, we have ideas of what work is, but physics will be a very different definition. So, in your everyday life, work would probably be where you go to make money, or if you're helping a friend or cleaning, you're doing work. But in physics, we're going to define it with energy and forces in mind. So let's have a look at this excerpt from the bright space. So if you think of what happens when a force is applied to an object, if there is a net force, we see an acceleration, and that acceleration will be in the direction of the net force. By making an object accelerate, we actually give it energy because we're going to give it kinetic energy. So energy is actually defined as the ability to do work. But let's look a little bit more closely at what is happening with the force and how it gives different objects energy, and then we'll define work. When we have a force, when we apply a force on a ball, like when we throw it, we actually give it the ability to travel through the air, and it could make a dent in the dirt when it lands. So there's a whole bunch of energy transfers happening there. We are giving the ball energy and giving it kinetic energy. And then as it falls and lands, it makes a dent in the dirt. So that is work. And that transfers energy to the dirt to make that hole. And the energy is also dissipated once the ball hits the ground. So it is easy to imagine that the bigger the initial force on the ball, the greater energy it has, so the farther it goes, and the deeper the dent when it lands. And if you think of an arrow and bow, the huge force used by a bow to accelerate that arrow is what gives the arrow enough energy to embed itself in the target. So we have in our last activity looked at different types of energy and how we can measure the transfer of energy. In this activity, we're going to be looking at work and the amount of energy transferred to an object by a force. So the definition of work in physics is that a force has to cause a displacement. An external force, I should say, has to cause a displacement, and that will give us work. So we write the equation for work as work is equal to the force vector, and this is a special type of multiplication. It's called a dot product. So the force vector dot product with the displacement vector. And don't worry, we will have a simple way of looking at that. So our force will be measured in newtons, and our displacement will be measured in meters. So work is measured in Newton meters, and that is joules, just like we saw in our last lesson. So Newton meters is joules, which makes sense because we know that energy is the ability to do work. So work and energy will have the same unit. I like to actually think of work as energy being transferred from one object to another. So this little dot here, normally in math we just say that's multiplication, but when we have vector dot vector, that is the dot operator, we will end up with a non-vector quantity. So work is not going to be vector. So even though we start out with force and displacement as vectors, work will not be a vector quantity. It is a scalar quantity with no direction. So let's look at some different types of work. So that dot product we'll talk about a little bit later, but there are different types of work. So for there to be work, there has to be a displacement. So we call the case where that force is acting in the same direction as the displacement positive work. So let's say we have a person pushing a box forward. The displacement is going to be in the forward direction, so that's my displacement. And my force is also going to be in the forward direction because the person is pushing forward. So this is positive work. Now let's look at negative work. So in negative work, there's an external force and a displacement, but they're in opposite directions. So that would be negative work. So if you do have that, an example would be, say I have a box that's sliding. So its displacement is forward, it's going forward, but as it slides, it's going to slow down due to friction. So the force that's slowing it down is friction, and it's in the opposite direction. So that would be negative work. So that's negative work because the box and the force are in opposite directions. We could even say that the angle between the box or the displacement and the force is 180 degrees, whereas this angle is 0 degrees between our force and our displacement. So we have positive work and negative work. Positive, we either have it moving at constant velocity forward and the force is forward, or it might be speeding up. And if you have negative work, you'll see it slowing down. So anything like a car hitting a wall, the wall is doing negative work on the car because it's slowing it down and stopping it. The last thing that we want to look at is this case of zero work. So there's, this is our bright space. There are a few ways that we might have zero work. So say I pushed against a wall and the wall didn't move. That means there's no displacement, so I would have no work. So if I have that case where a person is pushing against a wall and the wall's not going anywhere, there's no displacement, there would be no work. The same thing if you had no force, there would be no work. If you didn't push anything at all, then there's no work done. One case of zero work that is a little tricky is that if there is a perpendicular force to the displacement, that's also no work. So let's say you're moving at constant velocity and carrying a tray or a box. So if you're walking at a constant velocity, so you've already sped that box up, you don't need to push on that box anymore, it's already in motion. So you're actually just holding the box up. So this only works if you're just holding the box up, you're not pushing it forward. So your only force is up. And then the displacement, in this case, you're walking forwards. And that means that your force isn't actually causing the motion or directly involved in the motion. Your force is just holding it up. That box is already going at a constant velocity, so it's going to carry on with that displacement. The only thing you're not actually contributing to that displacement by holding it up. So that means that this angle is 90 degrees between the force and the displacement. And in those cases, your force is actually not contributing to the displacement, so there is zero work done. And this actually comes from that dot operator that we were talking about. What that dot operator does, it means that we actually take work and we multiply it by the force times the displacement to get work, and take the cos of the angle between the force and the displacement. So if you have positive work, cos theta is cos of 0 degrees, because that means positive work means that the force and displacement are in the same direction. There's 0 degrees between them. So that is just cos. If you take out your calculators and put cos 0 degrees in, you would get 1. So in this case, work is force times displacement times cos theta, which is 1, or just force times displacement. So that's positive work. If I have negative work, I'm going to have to, then cos theta is actually cos 180. And if you take out your calculators and put cos 180 in, it's -1. So that means that you would have a negative value of the force times the displacement. And I would get negative work. And then if I had 90 degrees between my force and displacement, this formula, work is equal to force times displacement times cos of 90 degrees. That cos of 90 degrees is going to be 0. So I'll have force times displacement times 0. It doesn't matter what my force and displacement are. Anything times 0 would just be 0. So those are the 3 cases of work. You can have other values of theta besides 0, 180, and 90. You might have something in between these, but we won't consider that in this course or in this unit. We'll just do these main 3. So I'm just going to summarize, when I have 0 work, there's 0 degrees between F and D. So we'd put cos 0. Here we'd have 180 degrees between F and D, and then we would have 90 degrees between F and D. And that will give us our positive, our negative, and 0 if we use this form of the formula. Let's look at some examples. In our first example, we have a weightlifter that's lifting a 140 kilogram barbell, and they're going to lift it 2.1 meters up from the floor at a constant velocity. So what we need to do is find the work of that weightlifter. So to find work, we want to use the formula. W is equal to F delta D times cos theta, and we're just going to, before we start, see if the force is in the same direction of the displacement. So the displacement is up. They're lifting it up. And they're applying a force up to do that. It's not slowing down. That's the other way that we know that it's negative work if it's slowing down. So the force is up. So this will be positive work. It's good to just do a quick check what type of work we have, and then we can find out what the work done is. Okay, so now that we know the type of work, we want to know the force they're using and the displacement. So right away, if I know positive work, we know that they're in the same direction, so that's 0 degrees, and cos theta is 1, or cos of 0 is 1, so I'm just going to simplify this to the work is equal to the force times the displacement times cos theta, which is 1, so I can just leave the 1 out. I know right off the bat, I do know my displacement. If I read through my question, the weightlifter, we know the mass, and we know how far up they're lifting it. So how far up is the displacement. So that 2.1 meters up is the displacement. We already accounted for the direction, so we can just, once we've done our analysis of positive work, we can just put our displacement in without the direction, because we've accounted for the directions with this cos theta. But the force, we don't know the force that they're doing that work with. So what we're going to do is do a quick free body diagram, and which might seem intimidating, but all of the free body diagrams when you're lifting something up are going to look the same. So when I'm lifting something up, you're working against gravity. So I'm going to have a force of gravity down on the barbell. So I'll just put that this is the earth pulling the barbell down. And then the force that's actually lifting it up is the normal force, or we could say the applied force, either would be fine, of the weightlifter on the barbell. So we can actually find the work of any force. We want to know the force that the weightlifter is doing. So we're going to use this force of the lifter on the barbell. We don't know what this force is, but we do know the barbell is 140 kilograms, so we know what this force is. If it's moving at constant velocity, what we'll do is assume that the force of gravity is the same as the normal force. And we did this when we did friction as well. So the normal force is equal to force of gravity, and that's going to be equal to mg. So I know my mass is 140, and I can figure out at 140 kilograms, I should say. So if I know the mass, I can figure out the force of gravity, and we're going to say because the lifter is lifting it at constant velocity, that's going to be the force that that lifter is lifting it up with. So you can grab your calculator and do this on your own, but we will just put in 140 kilograms, and then we'll use the gravitational field strength, which is 9.8 newtons per kilogram, or you might use meters per second squared. So if I do that calculation, I do get that my force lifting that barbell up equal to the force of gravity is 1,372 newtons. We're not going to worry about direction because they're in opposite directions. Gravity would be down, the normal force would be up. And then work is going to be equal to the normal force, the force of the weightlifter, multiplied by the displacement, and it's just going to be multiplied by 1 because cos theta will be 1 because we have positive work. So work is equal to force times displacement because we have positive work. And I can even put 1 in there, but you don't have to. So I'm going to take my 1372 newtons and multiply it by 2.1 meters. And that will give me 2,900 Newton meters. And we said that the unit for Newton meters is joules. So we can rewrite that as joules, which is our energy unit and work unit. Whenever you have a work problem where something's being lifted up, we'll always use the force of gravity to see what the force up is. So we'll have to first find that mg, and then we can use the force, assume the force up is the same as the mg, and we can easily find our work from there. Let's try one more example. In this example, we have a driver of a car slamming on the brakes, and the car's mass is 1,575 kilograms, and it's skidding. So the car comes to a stop after 25 meters. So the distance, how far it's going, is our displacement. So let's actually do a quick sketch of this. So we have our car moving forwards for 25 meters as it's skidding to a stop. So right off the bat, we want to see if we have positive or negative work. And if we have a slowing down or a stopping, then it's going to be negative work. So what force is stopping it? And it tells us in the question, the coefficient of friction. So it's the friction force that's stopping it because it's skidding and causing friction. So there's a backwards friction force stopping it. We don't know what that friction force is, so we'll have to figure that out. So our delta D is forwards, our force of friction is backwards, so that's negative work. So our whenever we have negative work, our cos, there's 180 degrees between our force and our displacement. So our cos of 180 degrees is going to be -1. You can try it out on your calculator and make sure. So when we do work is equal to force times displacement, cos theta, that's going to give us negative force times displacement. But we do need to know what our force and our displacement are. We know what our displacement is. It's 25 meters. But we don't know what the force of friction is. So what we're going to have to do is use our formula for friction. And that's the coefficient of friction times the normal force. So we have the coefficient of friction up here. We don't know the normal force. But we're going to use the same trick we looked at in the last question, and we'll use the force of gravity to give us our normal force, because the car is being pulled down by gravity but held up by the normal force. So we'll have to use our coefficient of friction, which is 0.97. And we'll have to use our mass and g to find our force of gravity, and then we'll say that's our normal force as well. So g is 9.8. You can use meters per second squared or newtons per kilogram. And the mass was 1575. We want to make sure that's in kilograms whenever we're using the mass. So let's start off with finding the normal force, and that is equal to the force of gravity. So I know that the force of gravity is equal to mass times that gravitational field strength. So I'll sub that in and find out what my force of gravity is, and we'll say that's equal to my normal force, because whatever the cart's being pulled down with, the ground is holding it up with the same force. So you can try that on your calculator. If you multiply that 1575 by 9.8, you should get 15,435 newtons as the force. That's a little bit too many digits, but we'll keep them and use them in our next calculation and just round at the very end so we don't round a whole bunch of times. Once we know the normal force, we can find the force of friction using our formula that the force of friction is equal to the normal force multiplied by this coefficient of friction, and that coefficient of friction just depends on what surfaces we have. So I'm going to then find force of friction is equal to that coefficient multiplied by the normal force. So 0.97 times 15,435 newtons, and you should get 14,971. Actually, we'll do 972 because it's 0.95 as your force of friction. And our last step, once we know the force that's causing the work, we can find the work. So whenever you have something slowing down due to friction, you will have to find the friction force with the normal force, and we can use the force of gravity, and then we can find our work. I'm going to take this version of work where we account for the 180 degree difference between the displacement and the force of friction. So work is equal to negative force times displacement. My force is 14,972 newtons, and my displacement was 25 meters. So my overall work is pretty big. It's negative 3,000, or 370,000, when you round it, joules of work on the car. And we know it's negative work because it's slowing down and because there's 180 degrees between the force and the displacement when they're in opposite directions, which gives us -1 for cos theta and puts a negative in for our work. So there are some practice questions to try on this to get familiar with using these, and some answers for you to check out as well. Good luck.